Hello friends, now we will discuss another important topic from MOSFET family, that is complementary MOS, and specifically we will be talking about complementary MOS inverter, that is CMOS inverter. We call it as CMOS inverter. CMOS inverter is basically the semiconductor device which is based on MOS technology, and it is used in digital circuits as an inverter. Very first part of the topic is construction and operation of the CMOS. This is the layer diagram of CMOS. In CMOS, we have a single substrate on which we have the multiple devices, multiple MOS transistors, you can say that is fabricated. Here we have the first part, which is nothing but NMOS. NMOSFET you can say. In NMOSFET, substrate is P. This is N plus, this is N plus, so the channel between N plus layers will be N channel. This is if you can see, this area is nothing but simply silicon dioxide layer. This is also silicon dioxide layer. This is also silicon dioxide layer. These layers are used to separate the different MOSFETs on the same chip. These are called sometimes insulating layers or insulation islands sometimes. Here the P MOSFET is fabricated by diffusing the N layers or the P substrate. This is called N well, in which we diffuse the P plus layers for the source and drain. So this part of the device, this is single chip known as CMOS. This part of the device is known as NMOS. This part of the device is known as PMOS, and whole unit is known as complementary MOS. Complementary MOS means it is the device which will be having both NMOS as well as PMOS. If you talk about the CMOS inverter, it is basically the connection of these terminals of the NMOS and PMOS. I repeat, this part of CMOS is nothing but NMOS, and this part of CMOS is nothing but PMOS. So we can have the connections of CMOS inverter on the basis of the connections of these terminals of NMOS and PMOS. So let us see the connections of CMOS inverter circuit. In CMOS inverter circuit, so let us draw the devices one by one. This is the PMOS and we have NMOS. This is the NMOS. This is gate terminal of PMOS. This is gate terminal or drain terminal, source terminal of PMOS. This is drain terminal of PMOS. This is drain terminal of NMOS. This is source terminal of NMOS. This is gate terminal of NMOS. So this is PMOS. This is NMOS. So I have drawn the symbol for this part of the CMOS, that is nothing but PMOS. This is NMOS, so this is NMOS. These are the terminals available here. For PMOS, these are the terminals. For just for clarity, I can say let this is nothing but S1, this is G1, this is D1, this is S2, G2, D2. So I'll say S1, D1, G1, D2, S2, G2, like this. Now let us see how to make connections of CMOS inverter circuit. In CMOS inverter circuit, the drain terminals are connected together, and gate terminals are also connected together. Fine. Gate terminals are connected together and drain terminals are connected together. We give input to the inverter at gate terminals and say that is Vi, that is input voltage. Fine. Output of the inverter is taken from the drain terminals which are connected together like this. This is output. Fine. The supply of CMOS inverter is given to the source terminal of PMOS and I will say it is VDD. Fine. Positive voltage. This source terminal will be connected to ground. So we will be using a single power supply, that is positive supply, given to the source terminal of the PMOS. The source terminal of NMOS is connected to ground. This circuit is known as complementary MOS or CMOS inverter. Now we will see the operation of CMOS inverter. Remember, in digital circuits we have only two levels of the voltage, either 0 or plus VDD. In any digital circuits we have only two voltage levels, 0 and the power supply voltage VDD at any point. Fine. The voltage 0 is ground, which is logic 0, and voltage plus VDD is logic 1. So we have only 0 and 1 in digital circuits. So in CMOS we will be having only two levels, either 0 or plus VDD, or we can say either 0 or logic 1. Now, so I will be taking only two levels of the input voltage VII. Either it is 0, that means it is connected to ground, the input terminal connected to ground, or VDD. So I will be having only two levels of the input voltage. So now we will be taking two cases. Case 1, that is I am talking about the operation part now. Case 1, input voltage is 0. Fine. So when input voltage is 0, I will remove this part now. When input voltage is 0, let us see what will happen in the circuit. When input voltage is 0, let us see the voltage between source and gate of the PMOS is VSGP. Remember, this is the positive voltage for PMOS. Why? Because it is positive, the VSGP I will be taking. Then this is the voltage which is VGSN, that N stands for NMOS. Fine. Similarly, voltage here I will be taking VSDP. Why? Because source is positive with respect to drain in case of PMOS. Similarly, this voltage will be VDSN. Why? Because drain is positive terminal with respect to source in case of NMOS. These are the voltages we have in case of the CMOS circuit. So when input voltage is 0, see this voltage carefully. What will be VSGP? VSGP is equal to, that is nothing but VS1 minus VG1. Voltage at this terminal minus VG1. What is voltage at S1? That is plus VDD. So this is equal to plus VDD minus voltage at G1, that is input voltage, and what is the input voltage? 0. So minus, I will say VDD minus VI, that is equal to plus VDD minus 0, and that is equal to, that voltage will be plus VDD. That's it. So the voltage VSGP is equal to VDD. Remember, in case of PMOS, that is PMOS, in case of PMOS, when voltage VSGP is more than the threshold voltage of the PMOS, then this PMOS will be on. What is the meaning of on? That is important point here to be understood. In digital circuits, the transistors, that is NMOS and PMOS, are used as switches. When device is on, it behaves like a closed switch. When device is off, it behaves like an open switch. So in this case, when MOSFET works in cutoff region, it will be like an open switch. When it works in ohmic region, it works like a closed switch. But remember, when MOSFET works in ohmic region, it is not simple short circuit as a closed switch, but it is a resistive switch. What is the meaning of resistive switch? Resistive closed switch. What is the meaning? Meaning is when the MOSFET is in saturation in ohmic region, it behaves like a closed switch, but it offers certain finite resistance, that is known as RD on. That is resistance offered by the MOSFET in on state. Fine. So here this VGSP is VDD. So this is definitely more than, so that voltage is definitely more than the threshold voltage of PMOS. And if it is more than threshold voltage of PMOS, this voltage is more than threshold voltage, so your PMOS will be on. And what is the meaning of on? Meaning of on is it behaves like a closed switch but offering certain finite resistance. If you draw the equivalent circuit of this, I will draw the equivalent circuit for this. Let us see what will be the equivalent circuit. Here I have plus VDD, this supply voltage, then we have the source terminal S1, and this is behaving like a closed switch, and that switch is nothing but a closed switch offering some finite resistance, that is RDS for PMOS. Resistance between drain and source, resistance between drain and source, that is RDS for PMOS, and this lower terminal is D1, I will say, and this is the output terminal V0. Fine. I hope concept is clear. The current here will be nothing but drain current. Fine. Now here there is important point. When this device is on, output volt terminal is connected to the supply voltage through this resistance, that is RDSP, that is the resistance offered by PMOS. Now what is output? Output voltage here will be, that is VDD supply voltage, this voltage. Fine. Assuming there is assumption. Assumption is what? Assumption is, if you take it, if you consider RDSP also, what will be the expression? Expression will be minus ID RDSP, resistance offered by this. But if this terminal is open, RD will be negligible, this drain current will be negligible. Remember, if this terminal is open here, there is no path for flow of current, but that clarity will come once we discuss this as well. Fine. Now I will come to this point again, provided I have the condition of, that is the operational condition of NMOS as well. We will discuss this point again. Now let us see case 2. Case 2 not case 2, that is case 1 itself. Here I was talking about the condition of PMOS. Now I will talk about the condition of NMOS. Fine. What is gate to source voltage here? That is VGSN is equal to VG2 minus VS2. VS2 is voltage at this terminal. This is connected to ground, so this must be definitely equal to what? 0. Vi I have taken 0, so this is equal to Vi minus 0, and that is 0 minus 0 means 0. So important point, gate to source voltage of NMOS is 0, and that is definitely less than threshold voltage of NMOS. So this means your gate to source voltage of NMOS is less than the threshold voltage of NMOS. And when this voltage is less than threshold voltage, this must be off. So for this voltage, when input voltage is 0, that means when input is connected to ground, 0 means ground. When input is connected to ground, your NMOS is off. Why? Because its voltage is less than threshold voltage. So here what I conclude, NMOS is what? That is off. Come to this equivalent circuit now. After V0, I have the terminal, that is D2, and NMOS behaves like your open circuit. So this is T2, this is S2. I am not considering this part, I am considering only this part. So interesting point here is, when input voltage is 0, it means when it is at logic 0, PMOS is on, offering some finite resistance, NMOS is off, behaving like an open switch. So now if it is open, this terminal is already open, drain current is 0. If drain current is 0, then what will be the voltage V0? That will be equal to VDD. So that means VDD minus 0 into RDSP, that is equal to VDD. Fine. So your output voltage will be equal to VDD. What is drop across this? What is this? This is PMOS. So drop across PMOS is 0. Now if you remember the characteristics of PMOS and NMOS, I will be drawing here, that is small characteristic. If you remember the characteristics of PMOS and NMOS, I take this as the drain current, I take this as the drain to source voltage. So in case of MOSFET, we have the 3 regions of operation. This is the cutoff region. Fine. We have another region of operation. If you remember, this is which region? This is ohmic region. If you have gone through the MOSFETs, this is cutoff region. And what is this? This is saturation region. Fine. So we have the 3 regions of operation of MOSFETs. Now when device operates in cutoff region, the drain current is almost 0. That is for this case. And when current is 0, that means that is just like an open switch. So in cutoff region, MOSFET works like an open switch. In saturation region, you can see, in ohmic region, you can see this region, your voltage across the device is small, depending on the point of operation. Voltage VDS will be small, current will be large. When current is large, voltage is small, that is what? Ohmic region. Or I can say when voltage across the device is small, that is ohmic region. Here only one condition is fulfilled, not both. Drain current is not large, it means drain current is small. Drain current is small, but voltage VDS is small. So it means that must be somewhere here, that may be the point of operation of this device. So in ohmic region of operation, there are two conditions: current may be large, but voltage VDS will be definitely small. So if the voltage across the device is small, voltage VDSP or VSDP or VDSN is small. Whenever these voltages are small, the device will work in ohmic region of operation, where it behaves like a closed switch offering a finite resistance. So here in this case, your PMOS works in ohmic region, NMOS works in cutoff region. So it is a closed, it is an open switch, it is a closed switch. Now if you see the characteristic here, I will draw what, that is I0 versus V0 characteristic. Let us see the characteristic. Here first let us see the characteristic of NMOS. For NMOS, what is the output voltage? Output voltage of NMOS, I am talking about NMOS. Output voltage for NMOS is nothing but that is same as VDSN. Fine. That is for NMOS. But simultaneously output voltage here is nothing but this voltage VDD minus VSDP. So this is VDD minus VSDP. Fine. Here drain current is this, drain current is this, and that is equal to I0. I will say I0. Fine. So if you draw the characteristic, let us see the characteristic of NMOS and PMOS separately. This is the characteristic for NMOS first. I will be talking about NMOS first. Fine. This is voltage VDSN. This is the drain current ID. Drain current ID, I will be saying this is I0. This is same as I0. Fine. Here in this particular case, your NMOS is in cutoff region. So if you see, this is what, same as V0. Your VDSN is same as V0. Fine. So your characteristic will be like this. I'm sorry, yeah, this is off. When this is off, your characteristic for NMOS will be like this. So that is the characteristics for NMOS. This is NMOS. Fine. Now let us see the characteristic of PMOS as well. If you see the characteristic of PMOS, this is the drain current, which is same as I0. This is VSDP. That is the characteristic for PMOS. In case of PMOS, your voltage is small, this voltage drop is small, but gate to source VSGP is equal to what? VDD. When gate to source voltage is large, the characteristic of, that is drain characteristic of PMOS is like this. Why? Because here VGSP is equal to plus VDD. You can go through the characteristics of MOSFETs. When gate to source voltage here is that is not GSP, I'll say VSGP. Fine. These are the characteristics for NMOS. Since it is working in cutoff region, so characteristic like this. In this case it is working in ohmic region, but when you talk about the characteristic is like this. Fine. But So somewhere here, maybe somewhere here, it will be equal to what? Plus VDD. VSDP will be equal to plus VDD. I am assuming. Fine. When VSDP is large. Fine. Now, instead of taking output characteristic, this is output characteristic, this is output, both are drain characteristics. But I have to draw the characteristic of CMOS, not MOSFET individually. The characteristic of CMOS will be I0 versus V0. I repeat, please understand. Here output voltage is V0. Output current is I0. So I will be drawing the output characteristic of CMOS. But here I am talking about output characteristic of NMOS first and PMOS. So by combining these two characteristics, I will be drawing the characteristic of CMOS. Fine. For which voltage? When Vi is 0. So now see the relationship for PMOS. What is V0? V0 is nothing but that is, you please see, that is VDD minus VDSP. So VDD minus VDSP. Now, when VDSP is 0, when this voltage is 0, so what will be when VDSP is 0, what will be V0? V0 will be equal to VDD. I repeat, when VSDP is 0, and this is VSDP, when VSDP is 0, then output V0 is VDD. It means this corresponds to V0 equal to 0. This point corresponds to V0 equal to 0 on output characteristic of PMOS. And when VSDP is equal to VDD, what will be output? Output will be equal to, when VSDP is equal to VDD, this will be 0. So it means this corresponds to V0 equal to plus VDD. That's it. Now what I mean to say is, this corresponds to V0 equal to 0. That means this point. And this corresponds to V0 equal to VDD. So somewhere here, maybe this may be plus VDD here. So that means that characteristic of PMOS will be mirror image. It will be going backward like this. This point will be here and this point will be here. So this point, when this point is shifted at origin, this is this, and when this point is shifted here, so the characteristic will be like this. So this is the characteristic for PMOS. Which characteristic? That is for CMOS we can say. That is known as load curve. We will call this as load curve. And this is of course characteristic of NMOS. So this is the characteristic of PMOS, but when it is inverted by using this for V0, we will call this as load curve, not the characteristics. And remember, both are connected in series. Drain current is common for both CMOS and NMOS, both PMOS and NMOS, and that is the only point where current is same for PMOS as well as NMOS, and this point of intersection of load curve of PMOS and characteristic of NMOS is known as Q point of CMOS. So this is nothing but I0 V0 characteristic. So I0 V0 characteristic when input voltage is 0. That is how you have the characteristic drawn, output characteristic drawn for CMOS when input is 0. Now let us see the another case. When input is, that is case 2, input is plus VDD. When input is plus VDD, see this voltage. When input is plus VDD, VSGP will be equal to VS1 minus VG1. VG1 is nothing but VI. VI here is now VDD, and when it is VDD, it will be equal to what? It will be equal to 0. This will be 0. Fine. Now, since VSGP is 0, this voltage is 0, so this is definitely less than the threshold voltage. And if it is less than threshold voltage, this voltage is less than the threshold voltage, that means PMOS must be off. It must be off. Fine? Clear? Now, output voltage will be, V0 will be, since it is disconnected, so we will not talk about output voltage here. We will not talk about output voltage. Why? Because it is not connected to plus VDD now. Fine. So we will not be talking about the output voltage at this point. Now let us see NMOS now. VGSN is VG2 minus VS2. VG2 is what? VI. VI minus what is S2? 0. So VI minus 0. But VI here is what? VI here is VDD. And when it is VDD minus 0, so it must be equal to VDD. So this voltage is VDD, VGSN is VDD, which is definitely more than the threshold voltage. So this is more than the threshold voltage, and if it is more than the threshold voltage, your NMOS must be on. Fine. And when NMOS is on, now let us see the conditions. This is PMOS, which is connected to plus VDD, and it behaves like open switch. I am drawing equivalent circuit here. It is open switch. This is PMOS now. I am drawing the equivalent circuit. Fine. Now your NMOS is on, so it must be offering certain finite resistance RD, SN. This must be output terminal, and this is connected to ground. Fine. If this is connected to ground, this is definite, there cannot be any current. Why? Because this is disconnected from the supply. The only source of supply was plus VDD. Since it is open, so output terminal is nowhere connected to supply. It is connected to ground rather. So drain current here must be 0. And if drain current is 0, then voltage drop across this, that is this voltage drop across the NMOS in on condition is 0, and when voltage drop across NMOS is 0 or very small, we can say, then voltage drop across the device is very small. It works in ohmic region of operation, offering a finite resistance. So when the device, when voltage is more than threshold voltage and voltage across the device, that is this voltage is small, the only region of operation is what? Ohmic region. We have discussed already that part. So it means your NMOS works in ohmic region and PMOS works in cutoff region, and this is the equivalent circuit for when the input voltage is VDD, or for Vi equal to VDD. That is the equivalent circuit. This is the equivalent circuit of the CMOS when input is logic 1. Fine. If you draw the characteristic here, let us see how to draw the characteristic. First, we will see the characteristics of CMOS and NMOS individually, and then we will combine together to find the output characteristic of CMOS. Right? So this was the characteristic of PMOS. Here. Now, let us see the characteristic. In case this is what? VDSN, V0, ID equal to I0. This is for NMOS. So here NMOS is on and supply voltage, gate to source voltage is VGSN. So this is VGSN equal to VDD. That must be the characteristic. When gate to source voltage is large, so that is the characteristic. Fine. But PMOS is off here. So if you talk about characteristic of PMOS, it must be like this. And remember, this is the output drain characteristic of PMOS. But if you see this, when VSDP is 0, V0 is VDD, it means this point corresponds to VSDP equal to 0, and this point corresponds to VSDP equal to 0 and V0 equal to VDD. What I mean to say is the characteristic will be flowing like this, and this is load curve of PMOS. This is characteristic of NMOS, and remember both are in series. So the only point of intersection where current is same for PMOS and NMOS is this, and this is Q point. And now if you see previous case, the drain current was negligible when input was 0, and in this case also this is Q point. This point is not a Q point. Drain current is again negligible. So when input is at logic 0, drain current is negligible. When input is at logic 1, drain current is negligible. So drain current is negligible in both the cases, or I can say output current is negligible in both the cases when for logic 0 and logic 1. Therefore the power dissipation in the device is negligible. That is the biggest advantage of CMOS. So power dissipation in CMOS is negligible, the most important point of CMOS. So this is how the CMOS works. I hope the operation is clear. Now in next lecture we will be going through the transfer characteristic of CMOS. So wait for the next video. Thank you very much for watching the video.